Can I start? Yeah. Okay, welcome everyone here in this second webinar. Thomas Love introduced you with this second webinar, and I suppose that you also followed or have seen the first webinar a month ago. This is the second one about the high impact weather summer course we produced for the EUMETCAL environment. And today, in the next hour, I'm going to talk about first a short summary of the so-called convection scheme we use at the daily base at KNMI in our forecast office. And then I will tell you something about the role, the importance of wind shear in this story, and its influence on the formation of organization of thunderstorms, also called convective modes. And then I will show you an actual case study of convection that happened over Central Eastern Europe. In this slide you can see that was last weekend, but that was the weekend before, so it was the weekend of the 24th and 25th of April. And after that case study, when we have some interaction and I ask you to annotate and to answer a few questions, then I go over to some specific knowledge about some hazards connected to the high impact weather phenomena, like wind gust, lightning, but especially convective wind gusts. That's I will pay most of my time on. Okay, then I will start with a short summary. Here you can see a slide I showed you a month ago in the first webinar, in which you can see more or less the basic motivation of using a methodology in which forecasters are able to use it basically everywhere. And the main motivation again is that you can use this method without losing any physical insight. So in the past we were tend to use all kinds of indices as a sort of estimate of the instability of the atmosphere and so on. But in this method, you are able to really, combine ingredients. You can see the cook cooking in his kitchen, and he is using all kinds of ingredients to make a nice supper or dinner. I can see in the background that there are maybe some difficulties in audio. I can see my John Havinga is already helping out.
Yeah, okay. It's fine. We got it covered.
Yeah, and basically when the right ingredients come together, anything is possible. And I will show you a short animation, which is, I think, a very nice summary of this methodology, this ingredient-based forecasting. As you can see in the lower part of this short animation the boundary layer. That boundary layer you need, of course, moisture. But that boundary layer is a lot of times kept by a so-called inversion. That can be a subsidence inversion, mostly at 5, 6, or 7,000 feet. But it can also be a ground inversion. And that inversion can be overcome by the sun, of course, by just the solar radiation, the diurnal variation. But if that is not enough, then you need some kind of upmotion. And that upmotion can be delivered by lift mechanisms. And you have a whole range of lift mechanisms. And as soon as that is enough, then you can have the process of upmotion where you can overcome the inversion again. And then you will enter the free atmosphere, so to speak. And that's in the upper part of this image. There you can see the so-called free atmosphere, where the amount of instability merely depends on the amount of CAPE, so the convective available potential energy. So this is in a nutshell a nice overview of the ingredient-based forecasting. Well, at KNMI, again, we started to make use of this forecasting convection scheme 5 or 6 years ago, in which you can see 4 steps. And I already showed you a month ago in the first webinar how to use merely the first step, that is the ingredient moisture, the ingredient instability, and the ingredient lift. And well, you can see a whole range of subjects in which you can look at observations, but also at the numerical weather output by investigating the 3 ingredients. Well, in this webinar, I will focus on the role of wind shear, because the wind shear is a sort of extra factor you need to take into account to determine the final convective mode of organization. And well, in this scheme, you can more or less see a few photographs. I will explain it to you in a few minutes. And based on the 3 ingredients and wind shear, you end up with some kind of organization degree. And from that part on, you can go over to step 3 and step 4, in which you study and estimate the different weather phenomena. And in this webinar, I will focus especially on the convective wind gust. Nowadays, in the non-hydrostatic limited area models, it's more or less really well solved, so to speak. But apart from that, it's, I think, very important as a forecaster, as a meteorologist, that you also use your mind by studying the different information portals, the soundings, etc., the observations, to understand why some wind gusts are really higher than other wind gusts. Well, if we look at the ingredient-based methodology, you can more or less look at the first 3 ingredients. That is moisture, that's instability again, and that's lift, what I already told you. And the challenge in everyday summertime convective forecast is that you search for a sort of overlap area. You also need some kind of wind shear, and that overlap area consists more or less of a combination of moisture, lift, and instability. And when you have enough wind shear, then you can finally find a sort of spot or an area where you have the ideal combination of 3 ingredients and wind shear. And in this slide, you can more or less also see some information to fill in the ingredients. So that can be very useful when looking at observations, but also at the numerical weather output. Okay, when I go over to the wind shear, I told you that the wind shear is more or less a sort of extra factor that you need to take into account to understand the mode of convection, which will be chosen by the atmosphere. And in the next sub-module, I will discuss with you something about the photographs. But I think for me personally, as a forecaster, which is very important, is to look at some kind of shear that's called the effective shear, and that's something different than the ordinary normal shear you can easily look up when you look at a sounding or a proc sounding. But it's important to look at the effective wind shear finally, and I will explain that to you. But first, something about vertical wind shear. We are talking about vertical wind shear. You also have horizontal wind shear, but in this case we focus on the vertical distribution of wind direction and wind strength. Well, when you look at some vertical profile, you can basically draw some vectors which is an indication of the strength of the wind. That's the most easiest way by looking at a wind profile, and by looking at the difference, you can more or less say something about the wind shear between two layers. For instance, between 1 kilometer or 6 kilometer, it doesn't matter. You can choose every type of layer in which you can more or less determine or calculate the amount of wind shear. But why is it so important? Well, in the end, wind shear, vertical wind shear is important because it delivers, or it acts as a sort of shifting between the updraft and downdraft. When you do not have any wind shear, then you end up with the so-called single cell convection. And that means that the updraft will be finally killed by the downdraft, because there is no physical spatial shift between the updraft and downdraft. And when you do have shear, then you have a separation. So this is an example of a single cell. That means that as soon as the precipitation process is started, the downdraft will be developed, and the downdraft will be in the same place as the updraft. So that means that this type of cell without or only little wind shear will only produce severe weather for a relatively short moment of time. And when you do have wind shear, then you have to look at the image on the right-hand side of the slide. Then you can see on the hand of some drawings, some red vectors in this photograph, that you can see clearly a shift in the updraft and in the downdraft. And this is, I have to admit, this is quite a nice example of really a shift in those two vertical motions. Well, a little bit something about the technical details. When we look at convection, you have to take into account a non-hydrostatic situation. So you deviate from the hydrostatic balance in the atmosphere. And you can imagine that, of course, because you do have accelerations in the vertical axis. So that means that you do not have a balance. So that means that there is something like a net force in the vertical direction. And that net force will particularly triggered by the so-called dynamic pressure perturbations. And to keep it a little bit simple, if you look at the image on the left, you can see the wind shear, unidirectional wind shear to start easy. From left to right, and you can see from the cumulus congestus clouds that it's bending towards the right, and you can see on the upstream side a little bit of a pressure perturbation developing, in the sense that there is a small high pressure perturbation, and on the downstream side you can see a dynamic low pressure perturbation. And it's interesting to finally look at atmospheres where you not only have a change in strength of wind, but also a change in direction of wind. And then you end up with, for instance, when you have a varying wind with height, with not only in the horizontal dynamical pressure perturbations, but also in the vertical. And that's the trick. That's really the trick to establish an atmosphere in a developing cumulonimbus cloud, where you can have very high accelerations upwards, but also downwards. And that makes it very important to look nowadays at especially the non-hydrostatic limited area model configurations, in which those dynamic pressure fall or perturbation is really calculated. Well, when you look at Shear, we most of the time we make use of a sort of diagram. I will show you that in a few minutes, that diagram, but you can more or less look up the amount of vertical wind shear you need for some kind of modes in convection. And you can see that for the low vertical wind shear, you end up with single cell convection. And when you enlarge the amount of vertical wind shear, then you have a more organization degree, like a multicell. That can be a line or a cluster. And when you do have very high vertical wind shear values, then you end up with the squall line or even a supercell convection. And you can see that in nature, you expect that there must be some kind of upper limit. Most of the time you end up with some certain particular strength of the developing updraft. That can be a weak one, that can be a very strong one for some time. And to study the vertical wind shear, the type of vertical wind shear more, then we can step over to the hodograph. And the hodograph has one big advantage, that you can more or less see on the hand of how the curve looks like. You can draw a lot more conclusions about the type of vertical wind shear by only looking at the wind profile you can see on the left hand side of this slide. And hodograph is nothing more than to place the wind factors on each layer onto an X and a Y scale you can see on the right, and to connect the points of the factors with each other, and then you end up with a curve in blue like this. And some different advantages, as I told you. You can look at the amount of wind shear, but especially you can also look at quite easily at so-called 0 to 6 kilometer wind shear. And that is a very important one, because the 0 to 6 kilometer wind shear seems to be a very important indicator for the type of mode of convection. And that's based on empirical data studies. That was done something like half a century ago, 50 years ago already in the United States. Based on the empirical data studies, they found out that the 0 to 6 kilometer wind shear, also called the bulk wind shear, so you take the absolute value between surface level and 6 kilometer, has a lot of information for using to estimate the mode of convection. Furthermore, you can also look at other model layers, which can be important when we finally look at the effective wind shear, which is in the end crucial for having a very representative estimate of what is happening in the atmosphere. But the hodograph is an important tool to have a vertical wind shear at a glance. But also, you have to study a moving storm in a so-called storm relative frame. That means that you go inside the storm and move with the storm. So you have to subtract your background field. And that means that when you move with the storm, you end up in a so-called storm relative frame. And that gives you a lot more information about how the vertical wind shear is influencing the storm itself. Here you can see an example of putting or placing the vertical wind profile into your hodograph. You can do a lot of things with it. This is an example in which you can combine it with the numerical weather output. So here you can see on the left-hand side something that comes out of your model, and yeah, most of the time that's, especially with nowadays numerical weather outputs, which is quite accurate, you can draw quite a nice or subtract quite nice hodograph. But now I'm going to talk about effective wind shear. And what do I mean with that? Well, in sounding, I think you can easily see the capping inversion. It's around 900 hectopascal. And that means that with developing convection, when this sounding is, for instance, occurring in the afternoon, then you have to skip more or less the information in the boundary layer, because you need to have some lifting mechanisms to have an eruption of convection above that capping inversion. So that means when you determine the mode of convection, you do not have to look at the boundary layer anymore. So in the lowest 100, 150 hectopascal most of the time, you can skip that part, and you only have to look at the amount of wind shear that is happening in the free atmosphere. So if you determine the amount of wind shear, then you have to start by looking at the top of the inversion, capping inversion, and then go upwards for 6 kilometers, for instance, to determine the bulk wind shear between the capping inversion and 6 kilometers higher in the atmosphere. And that gives you finally the more useful shear information to incorporate in your convective forecast scheme. Because it's a little bit of a small image, I realize that, but you can see on the right hand side the convection forecast scheme. I enlarged the 4 modes with the 4 hodographs, but on the right hand side you can also see an image which relates to the dependence of vertical wind shear and cape on the mode of convection. It's a rough estimate based on that empirical data studies in the United States, but we more or less copied this scheme, and we checked it with a lot of convective cases in the last 15 years, and we in Europe and also in the Netherlands, and we found out that it is useful, this type of scheme for instance for Europe as well. And you can see on the y-axis the vertical wind shear, on the x-axis the horizontal axis the amount of cape. And it's interesting to look at this type of information a little bit more in detail, because as you can see that the degree of organization, the convective modes, is important to study, because the level of hazardous weather or the level of hazards depends on that. As you can see, when we look at especially low shear situations, then you most of the time end up with single cell or pearl storms. When you increase the amount of vertical wind shear, then you end up with moderate or even good organization. And so the 3 ingredients in combination with the shear depends the convective mode. And I will show it to you in a little bit more detail on the end of this slide. Here you can see in this image the effective vertical wind shear on the y-axis, and on the horizontal axis again the cape. And I can tell you that that's also based on some actual research which is done in the United States but also in Europe, that finally the amount of effective vertical wind shear is more important than the amount of cape. So shear is more important, dominates more than the amount of cape. That means that only with some relative small amounts of convective available potential energy, but a lot of effective vertical wind shear, you can end up with quite vigorous convection. as you more or less can see in this scheme. A few points before I go over to a case study in which I ask you to answer a few questions. Well, you can read the text, of course. It's of great importance to identify the convective mode, and each convective mode has its own characteristics in terms of hazardous weather phenomena. Well, to give you a summary, CAPE is purely indicative. A wind shear is often more important, and you have to look at the effective layer. So you do not have to take into account the layer below an inversion, capping inversion. And it's also important that you realize that when you look at convection, that you also take into account the life cycle. But to start with a case study that happened 1 week ago, maybe you have noticed it, and maybe there are some participants in this webinar who encountered this convection because it happened in Hungary, Slovakia, Moldavia. And first question I have for you, this is the situation of the 24th of April during daytime. And you can see, first I will explain to you what you can see. You can see an overlay of HRV RGB image with 500 hectopascal geopotential height and mean sea level pressure, and in red you can see the so-called theta E at 850 hectopascal, the spatial distribution. And my main question is, and please make use of the annotate facilities, that you point out the area where you think convection will be released in the, let's say, the next few hours. And I will give you the allowed here. And I will do it for all. I will give you permission. Just wait a moment. Well, okay. I have some difficulties in to give everyone in.
Yeah, I thought I did select it. Maybe I missed some options. Sorry.
Yeah. But I gave some people permission, so they are allowed to annotate. But maybe you can use the chat as well, just to give. Yeah, right. Thank you. I can see that.
Yeah, sorry about this.
Yeah, they are coming in now. Well, you can see from the colors that most of you are indicating the more or less the same area, and that's the area. Yeah, also people are choosing a little different area, but I will explain it to you, of course. Because based on this information, and for your idea, I guess that most of you already know it, but within EUMETCAL, you are able to look at a map viewer. And in that map viewer, you can easily combine numerical weather output with satellite information. And most of you has indicate the right area where you can expect convection, because when you look at the upper air pattern, so the 500 hectopascal geopotential height, in combination with the theta E at 850 hectopascal, which is more or less an indicator of the amount of moisture you can have in the atmosphere that can be released. So it's a kind of latent energy format. And again, when you look at the upper air pattern in combination with an indication where you can find most of the moisture, then you have a sort of first clue, a rough estimate where you can expect that a lifting mechanism can act as a sort of triggering up motion to overcome some certain inversion. But it's only a rough estimate because you only have an upper air pattern and some theta E values, and of course also some mean sea level pressure. What you do need more is, of course, some specific information about lifting mechanisms. And I discussed already in webinar 1 that you need to focus on, for instance, areas of positive vorticity attraction, or you can finally look at the Q factor, which is a combination of vorticity attraction and temperature attraction, which tells you something about the amount of divergence. And divergence in the upper atmosphere means convergence in the lower atmosphere. So that's also a sort of basic information to find the areas with upward motion. But again, this is only a rough estimate. And it's correct because when we look at the next slide, and I will stop annotating. Oh, I need, yeah. Then you see that indeed this is the same information, but a little bit more zoomed in. And then you can see that over the area of interest, you can see that in that area between a ridge of an upper level ridge and a trough. The trough is located over Italy, over the north of Italy, and the upper level ridge is located here over the eastern part of Europe. That in between the trough and the ridge, there you find an area where you have probably a combination of the perfect overlap of enough moisture, enough lift, and then the question if you do have enough instability, and then you need some more information, and that is to say you need some information about CAPE. Well, I will show you that in the next slide, but before I go over to the next slide, I will show you the upper left image. That's the weather map, and you can see the weather map of the 24th of April for 12 UTC. You can see a frontal system with a sort of so-called triple point, in the sense that you have the warm front and the cold front, and somewhere at the meeting point of the warm front and the cold front, you have most of the lift. And when I go over to this slide, then I make use of a sounding that's based on numerical weather output, and I placed the proc sounding, the model sounding, in the image you can see in the upper part, where you can see the map of southeastern Europe. And just to the southeast of the low pressure area, I pointed out the location, Slovakia, just to the north of Hungary, where you can see the sounding, and you can see some numbers. You can see on the right hand side, you can see the SP cape, the surface based cape, the mixed layer cape, and the most unstable cape. And what is striking is that the surface based cape has the same value as the most unstable cape. And that's not so strange, because if you look at the sounding itself, then you can see that it is not capped. So more or less there is convection possible, which is feeded from the boundary layer. And that means that you can also more or less look at the amount of vertical wind shear all the way up from the ground. And my main question to you is that based on this information and based on this sounding, can you put in the chat very shortly, just one word, where you expect what kind of mode of convection you expect? So it's only a rough estimate, so I'm only looking at this type of information. So please add your answer in the chat. Okay, I can see a lot of answers, and it's interesting to see the whole variety of possible solutions that you give me. So it all ranges from single cell up to supercell. I can see that my colleagues from the JMG in Woensdrecht, John Havergaard, have chosen for the mini supercell. Well, let's find out. The correct answer will be, and I will go over to the next slide, that there was a in this environment that was able to produce the mode of multicluster or even squall line with some even some supercell characteristics. So that means if I go back to this slide, that if we look at the left upper image, then you end up with the upper part, and then a little bit more to the left of the middle, so the upper part of this image. So that means that you do have some cape, but not too much. But at the other hand, you do have a lot of vertical wind shear. And if we estimate the vertical wind shear, then we can start at ground level, where you have a southerly wind of 15 knots, and then you can go over to 6 kilometer height, 400 hectopascal. There you have 55 knots. It's unidirectional, more or less, a little bit of varying in between. But if you look at bulk shear as a sort of first estimate, then you end up with some 45 knots of vertical wind shear. So the 45 knots is enough to end up in the squall line or even in the mini supercell quadrant. And that was what that happened in this case, because you can see on this slide the combination of radar and satellite and the other numerical weather output information. And based on the radar information, you can see that, yeah, that mode of convection, it looks like a little bit of a developing multicluster or even some squall line habitus, and in between we can see that in the next slide there's also some supercell characteristics. At the same time, I produce a sort of vertical cross section, and you can see on this slide how I produce that. That's from southwest to northeast. And I cross the line of convection. And if we look at the bottom left image, then you can see the result of this vertical cross-section, where you can find a combination of equivalent potential temperature. And in this case, I have chosen for omega. So the vertical, the net vertical information, vertical movement information. And then you can see that there is, especially here over the area of convection, that there is some, even some synoptic lift. It's on a larger scale where you can find vertical motion. Well, this is a zoom in of what happens a few hours later after 12 Zulu. And you can see, based on a combination of satellite and radar on the left, that there was even a sort of embedded supercell, and that was interacting with a baroclinic zone just to the northeast of it, and that possibly produced a short duration tornado on the ground on that particular moment. Well, this is a day later, and a day later again over the southeast of Europe, over Moldavia and Ukraine. You can also see the eruption of convection and even some supercell convection. And in this case, I combined some Q factor information with satellite information. And the Q factor again combines the influence of temperature advection and vorticity advection. I have to say that in this online training for EUMETCAL, I merely focus on both the distributions. So I focus on not only vorticity advection but also apart temperature advection, to find out where you can expect most of the vertical motions. It can be ascent but also descent motion, of course. But on the day after the 24th, on the 25th of April, also some vigorous convection took place, and yeah, that was more or less the first interesting summer look time convection this spring so far. And this is the belonging sounding over the western part of Moldavia, and you can see again a combination of not too much cape. That's in the range of 400, maybe 500 joule per kilogram, and in combination with, for instance, 0 to 6 kilometer wind shear in the range of 45 or even 50 knots. But when you look carefully at this sounding, you can see a very small capping inversion, and that's around 750, 800 hectopascal. And I pointed out this location because this was on the border between where convection was possible, and especially to the north of it, the capping inversion was not there. So convection could easily develop, but south of it, the capping inversion was a lot more developed. So that means when you look at this satellite image, you can see that in the southern part of Moldavia, you did not have any convection at all. So it was especially on the central and northern parts of Moldavia into the southern part of southwestern part of Ukraine, where you end up with some vigorous convection. This is the radar, which you can see quite nicely most of the time the squall line modes that developed over that area on the 25th of April. And this is sort of overview of the 0 to 6 wind difference. So you can easily see the highest amount of bulk wind shear between the Earth, between the surface and the 6 kilometer height. Okay, to give you a sort of summary before I go over to the next topic. When you have lift and moisture and instability, to start with lift, you have to look at, of course, lifting mechanisms like positive vorticity advection. It can also be outflow boundaries, and especially when you look at the boundary layer, then it is also important that you look for moisture flux convergence. So that's a combination of moisture axis and mass convergent axis, so to speak, officially. So you can look at streamlines in combination with moisture content. So streamlines and theta E values, 850 hectopascal, give you a sort of first estimate. If you are living in hilly areas, then of course you also have to take into account the relief, the topography, the hills, the mountains. And again, when you look at moisture, the theta W or theta E values are quite nicely, give you a quite nice information, as well as advections. And advections can be sometimes tricky. When you look at some actual overviews, then you have to take into account, for instance, some local enhanced or local mesoscale circulations that can produce advections of extra moisture. In the Netherlands, in our flat country, it's for example important to also take into account the sea breeze or even the IJsselmeer breezes that can lead to some extra moisture convergence. And again, when you look at instability, you have to look at the type of soundings to start with, and then to decide which type of cape you can choose. Is that a mixed layer? Is that surface-based? Or is that most unstable cape? Well, now I go over to a small module that's concerning something about the high impact weather phenomena. I do not have the time to discuss everything, but I will especially focus on the wind gust and a little bit about the excessive precipitation. And if we look at the ordinary cell or the single cells, then I showed you that with very less vertical wind shear, you only have a relatively small duration cell, which typically ends after, let's say, half an hour or 45 minutes. And what is very characteristic that in the environment you do normally have low cape values. When you do have high cape values, then you end up again with single cells. But then those cells have stronger vertical motion, so we also call that pulse storms. And how does it look like? In the upper part, you can see more or less the theoretical schemes. And in the lower part, I embedded a few radar images of a single cell convection that happened in the Netherlands. You can see the time frame. It's 1400 hours on the lower left radar image, and then in a few time steps you can see the development of the single cell. So that means that you have an eruption of convection based on a strong updraft, and then finally after a relatively short time you do have the downdraft that kills the updraft, and that brings the storm single cell that can be a pulse storm again in a dissipating stage. So that's a very short duration. But again, when you cape, like in this example, you do have cape values above 1000 joule per kilogram. You can have quite vigorous severe weather phenomena, like a large hail, a lot of precipitation, and convective wind gusts. Well, I will skip the large hail, but I will pay some attention to excessive precipitation. That's more or less depends on two factors. That's the rain rate and the duration. That depends the amount of precipitation, as you can see in this simple relation. Well, if you look at the rain rate, you have to look at the environment, the atmosphere itself, in terms of combination of cape and precip water. And precip water gives you a sort of clue how much water can be subtracted from some certain atmosphere, and based on observations, but also based on numerical weather output. Nowadays, as a forecaster, you can more or less have a sort of overview in advance of the amount of possible water that can be produced by a cumulonimbus cloud. And again, when you look at the amount of precipitation, then not only CAPE and water is important, but also the duration. And duration of a storm depends on different kinds of factors. That's your background field, wind field. So that steers the storm. So the storm motion, the effective storm motion is important. And as a sort of interaction of your background field with the storm, you end up with a few possibilities in which the duration of the storm at one particular location occurs. You can have storms that move by quickly, so that means that even the fact that you have a very active storm, that you end up with some low precip values at your location. But sometimes you do have a sort of combination of cell motion and propagation that depends on the amount and the type of vertical wind shear that can lead to a so-called backbuilding. So the different cells are moving to the east in this example, but the propagation of the whole organization is the other way around. So the individual cells are moving to the right, and the system itself is a little bit moving to the left. So you end up with a situation that you, at one location, you do have continuously the formation of the new cells. And so that can be tricky because that leads to very to flooding, for instance. So that can be a tricky situation. That's backbuilding, and on the right hand side you can see an example of echo training. And then you have a cell motion to the right, you have a mid-level wind shear factor to the right, and then you have a moist low-level flow that comes from the south. And then you have parallel to your baroclinic boundary, so to speak. It can be a frontal zone. That's most of the time a frontal zone. You have the continuous generation of cells. And that means that when you are located somewhere parallel to this baroclinic boundary, you can also end up with a lot of precipitation. Okay. And in the end, also, you have to look at the topography or orography, which can also lead to flash flooding. And we had a very extreme example last year in 2021 in Germany and Belgium, and also in the southern part of the Netherlands, when also the topography played an important role. Okay, apart from single cells, pill storms, apart from precipitation, also the wind gusts are very important. And if we start with the wind gust produced by, let's say, a pill storm, you can look at three main terms. That's the decape. That's a term that depends on the amount of entrainment or evaporation. So you have water loading. So more or less the air is sucked downwards because of the enormous amount of precip that is producing, and that's falling downwards. And you have the so-called vertical transport of horizontal momentum. And that's nothing more than you gain some of the upper level winds downwards. Well, if you look at those three factors in detail, then for the evaporation, for the decape values, you have to look at the lapse rates and also look at the environment. When you do have a very dry boundary layer, for instance, That means that a lot of evaporation can take place, so that helps air parcels to cool extra down in the lowest few kilometers. So that's very important. When you look at the water loading term, you have to look at soundings or environments with which are saturated, which means that you can have high PW values in combination with high K values. So that leads to the most water loading influence. And again, when you have a very high wind shear, vertical wind shear situation, that means that you have most of the time very high wind speeds in the upper levels. Then you also have a high vertical transport of horizontal momentum. Well, if you go over to the multicells, then you have some more vertical wind shear, of course, and that means that you have a much larger time span. And I will pay some attention to it, because when you do have vertical wind shear, that means that you have a displacement of the updraft in comparison relative to the downdraft. And in this image, you can see a sort of mean shear factor that's pointing from the left to the right. And you can see the development of convection on the downstream side and not in the upstream side. And I will explain to you why this is happening. So for multicells, when you look at multicells and you make a sort of vertical cross-section, and you are aware of the type of shear factor, then it is always the case that you only have retriggering of new convection, daughter cells, only on the downshear side of the OFB. OFB stands for outflow boundary, and not on the upshear. And that has to do with the fact that you have to combine both the environmental vorticity that is developed in your environment in combination with vorticity in the cold pool. And you can see on the right hand side, when you have, for instance, a unidirectional wind shear with an increase of winds with height, then you can see on the right hand side two vorticity couples. One that is developing in the free atmosphere, that's on the right hand side, and you can see a sort of rotation couple, rotation that's developing in the cold pool. And when you look carefully, then you see that those rotation directions help each other. So that means that in the middle, some extra ascent motion can be expected, as you can see in this slide. So now I compare the theoretical right-hand side with the more practical image you can see on the left-hand side. So that means that on that side, you do have rotation couples that help each other. And on the other side, that's on the upstream side, we do have our monthly alarm. Maybe you can hear it here on the background. And it's fortunately it's a test. I hope this is not too disturbing to you, but I will talk further. So this is on the downstream side, but if you look at the upstream side of this multicell, then you end up with rotation couples that will not help each other. So the cold pool rotation will not help the environment rotation, and that's the main reason why you do not have the development of daughter cells on the upstream side. Okay, now something about the multicell squall line. You can see more or less a sort of upper view, in which you can see two different situations. You can see a situation along a frontal boundary with upper level winds which are parallel. That's on the upper left hand side, and then the right hand side, the lower part of this slide, you could see upper level winds, relative winds, which makes an angle with your boundary, with your baroclinic boundary. And the theory is that for having quite vigorous convection in the form of a squall line, you need to have upper level winds, which makes an angle with your baroclinic boundary. And only in that situation that can lead to a more vigorous squall line, while in the parallel case, you also have convection, which can be quite active, but it will more or less runs parallel to the front, and it will not develop into a squall line, in which you can see the second side with an upper level winch, which makes an angle with your front, in which you can see nicely the updraft and the downdraft in this animation. And you can see the continuous generation of new daughter cells on the downstream side. So that means that on the downstream side, together with the movement of your frontal system, of your squall line, that the net effect is that there is a squall line with literally a line of convection that moves from one direction into the other direction, from one point into the other point. Well, I can go over to, we still have a few slides to discuss. When do squall lines become severe? Then you have to take into account two factors. That's the flow speed at the top of the inflow layer. That's most of the time 2 or 3 kilometers above ground level. You have to look at the flow speed itself, but on the other hand, you also have to take into account the cape, and to give a sort of estimate of the strength of the downdraft. And so I already told you that you have to look at different kinds of factors. So not only the upward motion is important, but also downward motion, to have a sort of clue how active such a squall line will be. Well, if we look at the squall line itself, I think most of you have already seen such beautiful images in the past. When looking at the forefront of an approaching squall line, then you have some extra factors that can lead to an extra higher amount of wind gust. And one of the factors is that sometimes a real inflow jet will develop, and that can lead to some extra amount of wind finally at the ground. And those rear inflow jets are very important because that can end up easily 15 or 20 knots up on your estimated wind gust based on the other factors. So rear inflow jet merely evolves when you do have a cold pool and still a warm environment. And on the edge of the cold pool and the environment, also due to some extra pressure perturbations, an extra wind jet develops, most of the time at 1 or 2 kilometers height. And that will lead to an extra wind jet. And apart from that, also on the mesoscale, when you zoom in, and you can also sometimes see some extra rotation points on the edge of the outflow winds with the environment. And those mesoscale vortices can also produce an extra amount of wind. And especially on the northern part of the bow echoes, the so-called bow echoes, you can find the most aggressive mesovortices. And those mesovortices are producing a lot of extra wind, and most of the time, most of the damage when a squall line is passing by. And it's in the literature already known for many, many years. And again, in the United States, a long time ago, they start to develop conceptual models based on this theory. Well, to end up with a few slides about the most aggressive mode of convection. That's of course the supercell mode. You need a combination of high wind shear values and a lot of cape. And the difference with the other type of motions is merely that you have a rotating updraft. So a spiraling updraft instead of the more non-rotating updrafts connected with the other modes of convection. Well, that leads to vigorous, hazardous weather. Again, you need high amounts of vertical wind shear. And well, I can tell a lot about it, but there's no time for that. But you can look some more detailed information you can find in the online course. And now I end up with questions. So I will stop sharing my presentation so I can see you and also see the questions that I invite you to ask your questions in the chat. And if there is time, I can also answer some questions real live with your mic on.
If you want to be unmuted, just raise the hand. Yeah, thanks for the presentation.
Yeah, was the alarm disturbing that happened?
Just a bit, yeah.
Yeah.
It was noticeable. Yeah.
Yeah,
it's fine.
I forgot to close my window, but it's the first Monday of the month, and that means that at 12 o'clock we do have an alarm. And so my colleagues at the EUMETCAL, I think they have heard the alarm as well. Yeah, okay, John. I realize that this is a lot of information. Yeah, John, go ahead. Tomislav, can you unmute John?
Yeah, 1 second. We'll find him.
Yeah.
It's a lot of names. Yes. Go ahead.
Hello?
Yeah, hello, John.
Can you hear me, Rob?
Yeah, I can hear you clearly.
Yeah, if you could put on the slide with that you showed with the abbreviation or the summary with the pictures about the different modes of convection. The one that makes the difference between supercells and multicells. Oh yeah, it's completely on the beginning.
Oh, it's on the beginning, okay. Even kijken. This
the convection mode, the slide number 17 or
17. Oh yeah, that's this one. Yeah.
This one, yeah. So my question is, if you look at specifically to the pictures of the hodograph on the convection mode, you see pictures like the multicell and squall line.
Yeah.
And could you tell something about giving a little direction about what kind of wind veering is necessary? Because if you see at the wind speeds, sometimes are equal when you have multicells or squall line, and supercells. Sometimes the wind shear in knots is the same, but the actual difference is a supercell can develop when there is a wind veer. So could you give some clues or hands-on about that wind veer that's necessary?
Yeah, thank you for your question. I think it's a very good question, a very practical question where forecasters are dealing with. John, I will jump over to this slide to use it as a sort of guidance to answer your question. I admit that when you do look at the difference between multicell cluster and squall line mode, that it is a very subtle process that sometimes a multi-cell cluster, which cells are moving parallel to a baroclinic boundary, can sometimes convert into really a squall line segment, which moves away from one point in time, and that has to do with how accurate the steering background flow is more or less making an angle with your line of convergence, and mostly the line of convergence is the same as a frontal system or cold front or a trough. But that means that when it differs a little bit, when it changes a little bit, that steering flow, that can be in the upper levels, but it can also be at 700 hectopascal or 600 hectopascal. It depends a little bit on the depth of the convection, which type of steering flow you choose. But it merely depends on finally the interaction that takes place between the background field and your convection, and that depends on basically the angle, the wind shear factor, but also the upper level winds makes with your line of convergence. So that means that you can start with sometimes with just a multi-cell cluster, and you end up with a squall line. And that means that in the course of the time, in the environment, you can see that the winds, the upper level winds, for instance, are varying a little bit, so that you end up with an ideal configuration that the squall line can develop. I hope that answers a little bit your question. I think I also give you the clue that there is not an exact threshold that you can look at, but it's more or less, monitoring the convection and looking at, how well done the steering currents are interacting with the convection. And another way of saying that is that you monitor your wind pattern, in a sense that you look for a difference in the angle that the upper winds are making with your conversion line. And again, when you start by looking at slide number 17, and you look at the photographs, then I have to admit that sometimes the difference in the photographs are not that much between a multi-cell cluster and a multi-cell squall line, but it's a very subtle process in which indeed a squall line can develop, or not develop.
Well, thank you, Rob. You did I think a good explanation that there's not really a threshold, and that even multi-cell or maybe just speech here can create a multi-cell line convection, and it will become a squall line eventually in time. Yeah. Could you also say that a squall line, when it's happening, can also turn into a supercell in time, following that same thought?
Yeah, more or less, but that's a very difficult one, I have to say, but because it can happen that, and that was also the case on the 24th of April, that over Slovakia, that you start with a multi-cell squall line mode, and then embedded, there was for some short time also the development of a supercell. And that has to do with, finally, with the interaction the squall line has with the environment. And you can start, for instance, with the squall line mode, and then after some time, when that squall line is moving into an environment where you do have, for instance, a lot more varying with the wind with height, then you can end up in an atmosphere where a supercell can develop. And then it's not a solitary supercell on its own, but it's clearly embedded into the squall line itself. But I have to say, based on my own experience, but also from my colleagues at KNMI, but also from the other forecasters from ESSL in Europe, but also in the United States, that it's still a very difficult subject, in the sense that as a forecaster in your forecast offers, you most of the time are not able to give a perfect forecast on when parts of the squall line will turn into a supercell, so to speak.
Yeah, yeah. Okay, thanks a lot for your explanation, Rob.
Yeah,
and
nice talking to you, John, after so many years.
Yeah, dankjewel.
yeah. I know John from my formal company in the 90s, in the last century, when we worked at the Meteor Group company. So in those times it was called Meteor Consult in the Netherlands.
Yeah.
Okay. Okay.
There is one question in the chat.
Yeah. There's a question from Alina.
Alina, yes.
Yeah. You mentioned in the beginning there is a limit to the wind shear amount. I imagine that at some point shear will be too large to sustain the cumulonimbus and will break them apart. Could you estimate these threshold values? That's again also an interesting question, Alina. Thank you. Now the answer. Indeed, it is the case, especially in the beginning of convection, that when you do have an atmosphere with not that much moisture, then the first cumulus towers that develops are quite small. And in that time frame, you can have a situation that the vertical wind shear is so high that the developing cumulonimbus cloud will simply break down. So that is really the case. And but that happens in the starting phase. When you do have a lot of moisture in your atmosphere, then most of the time the cumulus towers will merge together, that will evolve into a large cumulonimbus complex, and that will not be so much negatively influenced by a high amount of vertical wind shear, in the sense that it will break down. And now your question about these threshold values, I do not have really a threshold value. Again, it depends largely on the amount of moisture you have, and also the spatial extension of your convergent area. When you only have a very localized convergence and a little moisture, then cumulus towers will break down because of the high vertical wind shear amounts. But when you do have more moisture and also a large area with acid motion along a convergent line, for instance, then you end up with vigorous convection which will not be influenced by some breakdown effects. Yeah. Is that clear to you, Alina? Yeah, okay. And Vladislav, he wrote that, I have to say it was not so convenient to you. Sorry about it, about the alarm, because, as we know, in Ukraine and also in parts in Moldavia, it's a very hard fact that alarm is not testing, unfortunately. Okay.
There was one question. Is the presentation going to be available? So the slides.
Yes, I can not only this slide, but also the slides from a month ago. I will put them onto the Moodle this afternoon.
Okay,
so
great.
People can make use of it. So as you already know, Tomislav also recorded this session, so that will be available. But also the PowerPoint presentation itself will be available from this afternoon on.
I don't see any other question.
No. Okay, it was a pleasure for me to give you this presentation.
Thanks a lot.
Again, and for the participants, when you do have questions, John Havinga is asking, is that on the website? Yeah, maybe John has to precipitate for the online course environment. And that's for all the participants. You need to have access to the online course, because you can find a lot of information in terms of reading material, but also a nice quiz, etc., etc. And then you can find my presentations as well. They are not there yet, but I will put them there in the afternoon. There's another question. Which units you showed wind shear intensity meters per second? Yeah, if you look at wind shear, it depends on the depth of the layer, but you can it's meters per second per length. So that means if you look at the 0.6 kilometer wind shear, then it has the unit of let's say knots. You can choose between knots or meters per second per in this case per 6 kilometers. Yeah, okay, thank you. Yeah, I think we are done now. And again, if you do have questions, you can use the form, and so that I can have a sort of signal that I can also ask further questions.
There is one more. What's the impact of the wind shear in aviation?
Yeah, that has, of course, its impact. Merely the aviation, it's important to look at vertical wind shear, but also horizontal wind shear for clear air turbulence can be important. So wind shear in both directions, so horizontal but also vertical, can produce turbulence. So that's the direct result of having wind shear, that it creates turbulence, and that's, of course, that can be very nasty for an airplane. Yeah. Oh yeah, surface monkey. Yeah.
Yeah. So yeah, I think we are at the end of the time.
Yeah.
So thanks for the presentation. I'm going to stop the recording.